Okay, good morning, everyone. Welcome back to this AstrotwinColo School 2020. We are back with Aurora Caselli. She's the teacher of this week, and we will continue the subject that we started yesterday, which was very interesting, by the way. And I was even planning to do myself all the exercises you did in the lab. I just don't have the time right now. And I know that they will be online available, so I will try to do it later. So thank you, Laura, for being back with us. And please go ahead.
Great. Okay, thank you so much. Hope you liked the first day of lectures. And for today, before we start, I just wanted to say that I will share all of the slides that I've been using at the end of the week. It's just through Google Slides, so I'll share those if anybody's interested. And also, I think that we'll do a office hour on Thursday at 2 p.m. Columbia time for an hour. If you're interested in meeting with me to ask any questions, you can just send me an email and I will send you a Zoom link and we can set up a meeting time in that window. So yeah, if you're interested, send an email about meeting times on Thursday. Okay, so now I will share my screen. And I just wanted to quickly look at the slides from the first day to remind you where we left off, and then I'll share my slides for the second day. Okay, so from yesterday, we talked about the resolution of spectrographs, and we talked about how the resolution basically sets the wavelength spacing. And high resolution spectrographs have a resolution of about 25,000 or above, which means that they have wavelength spacing of a few kilometers per second in the visible and near infrared. And then we talked about how a spectrograph consists of something that separates the radiation by its frequency or wavelength. So that's a spectrometer, and then something that you can use to detect that radiation. And we talked about how at high resolution, we use Echelle gratings, which basically prioritizes higher orders. And the higher the order, the more separation you're going to get in the wavelength space. So here you can see at the first order, you get a little bit of separation, and at the second order, you get even more separation. And in reality, what happens with spectrographs is the light comes in for high resolution spectrographs. The light comes in and we hit the first Echelle grating. This initially separates the light into its different wavelengths. And then we go through a cross disperser, which even further separates the light by wavelength. And this also allows us to put multiple orders onto a single CCD. And then we talked about how CCDs have much better quantum efficiency than any of the other instruments that we've used before for detecting lights. So photometric plates or the human eye, just looking at a telescope. And we talked about how in the near infrared and the optical, you need to use a different CCD. And that's just because of the way that a CCD works. When a photon hits the piece of metal, an electron is emitted. And the type of metal depends on what energy photon can release a electron. And so for near infrared, you have to be really careful because you don't want thermal photons coming from surrounding material to be able to have the exact same effect as a photon coming from your telescope and coming from your object. So near infrared instruments have to be kept really cold. Okay, great. That's all the review I wanted to do for yesterday. And then I will share the slides from today. Okay.
Correct. So I use toggle, and then what I do is I have.
Sorry, I had to get the new tab. Okay, great. So today, now that we've learned the basics of how spectrographs work, I'm going to talk about what you actually do when you're observing in high resolution. So what type of calibration frames you need to take, and how you use those calibration frames to go from the image on the CCD to the spectrum that you actually are going to use. Okay. So let's start with this picture, which I already just showed. But we have over here, we have what we would see on the on the CCD. And if you remember, we have the each row here is a different order. So we have the M order, and then we have the lower orders, so the M-1 orders, and the higher orders, M+1 orders. So we've projected all of these orders onto the CCD. And what this looks like in real life, or when you look at a picture of a CCD, is something like here on the left. So we have all of these orders in light colors, and then there's space between the orders, and these are dark. And so today we're going to be talking about how you go from this image to what you see over here, which is the spectrum of a star that you're used to, the one-dimensional spectrum of the star. So we have flux on the x-axis and wavelength on the, flux on the y-axis and wavelength on the x-axis. So the steps that we're going to be talking about today are how to correct for dark current, how to correct for variations in the response of the CCD. And so that basically just means, do different areas in the CCD produce different numbers of electrons if they are given the same amount of light from photons? Then we're going to talk about how you trace those orders, each of those orders, and extract the spectrum from each order. And then we're going to talk about how you can remove any background from the sky. And that's only necessary in, it's mostly necessary in the near infrared. And so we'll talk about why, and then how to remove it. And then we'll talk about how to get the wavelength solution. And so if you go back here, we can see that we have all of the different orders, but we have no idea what wavelength corresponds to what pixel. And so we'll talk about how you can use different calibration frames to get a wavelength solution. And then lastly, we'll talk about post-processing steps. So this is after we have a 1D spectrum, how do we make it look better? So we can combine orders to make a single spectrum. We can correct for Earth's atmosphere or the tellurics. We can correct for any shape of each order, which is called the Blaze function or a Blaze correction. And then we can correct for cosmic rays. And so this is what we'll be talking about today. Okay. So the first step is the darks. And if you remember, we talked about how CCDs, you need to keep them cool so that thermal photons don't excite any of the electrons, which would then be counted by the CCD as flux. Even if the shutter is closed, this would happen. And so this is a basic consequence of how CCDs work. There's always going to be some dark current, and we need to remove this. So here's an example, and all of these screenshots that I have here are from an observing run that I've done on the IGRIN spectrograph, which is the same optical layout that I showed you yesterday. So it's a resolution 4,500, 45,000, and it's near infrared, so H band and K band. And so there is a significant amount of these hot pixels or bad pixels because near infrared detectors have more of them than optical detectors. And so what the dark current is all these little dots on the detector here. And so in order to remove them, what you normally do is you take exposures with the instrument shutter closed. So you don't actually let any light go through the slit. And you take those for the same amount of time that you'll be doing your observations for. So say if you plan to do a 200-second exposure on your target, you also want to do a 200-second exposure for your dark frame. And then to kind of average out any weird effects, you repeat this 5 to 10 times. So you take 5 to 10 dark frames. And then what you do is you want to median combine all of those. So average them together and get kind of your average dark frame. And then from every other frame that you're going to use for the rest of the observations, you always want as your first step to subtract this dark frame. Because no matter what, we expect some sort of dark current to be here. And that's what we're seeing. Okay, so now we've removed any dark current. And next we want to remove, next we're going to take flat exposures. So what flats correct for is any gain. And what the gain means is how many photons it takes to convert to how many photons it takes to excite your electron. And this changes based on where you're looking on the CCD. And so kind of you can easily see that the edges of the CCD have less gain than the center. And this is taken by uniformly, you open up the slit, you let light come in, and you take a picture of a screen that is being uniformly illuminated by a lamp. So the screen should have the same number of photons across the whole thing. And so if the CCD was perfect, you would see the same amount of light at every point in each of the orders on the CCD. But we see that that's not the case, and so we do have to correct for that. And that's what the flat is correcting for. Okay, so the usual procedure for the flats is you take an exposure of the screen that's being uniformly illuminated, and it's usually being illuminated by a halogen lamp. And again, to make sure that we don't take one weird exposure, we repeat this 5 to 10 times. And then for each of those 5 to 10 images, like I said before, you want to subtract the dark frame from each of those. And then you combine all of those together in the same way that you combined the darks using a median combine. And then we want to make sure that we're not changing the counts actually in the over the spectrum. And so what we do is we normalize this so the median value is 1. So something over here is going to have a higher value and something over here is going to have a lower value, but the average is going to be 1. And then we can divide every target image by this. And this should take into account any changes in the gain. So any changes in how the CCD responds to photons on the sides versus in the center. Okay. So the next thing that was on our list is taking care of the sky background. And I'm showing you 2 images. One is the night sky in visible bands, and the second is the night sky in near infrared bands. So you can see in the visual bands, basically the night sky is mostly dark. We have a little bit of light on the horizon, which is normal. But then we have dark sky and stars. In the near infrared, this is completely different. You see kind of these banding structures, And this is known as air glow, and it's mostly caused by OH emission in the atmosphere of Earth. So this is Earth's air glow. So the sky is bright in the near infrared where it's not in the visible. And what this looks like on your actual spectrum. What this looks like on the actual spectrum is here we have our order from our target. So this is the spectrum from the target. Oops. And then where I'm pointing with this arrow, you have kind of these emission lines. And you know it's an emission line because we have light. So on all of these images, anything that's whiter means that there's more flux. And anything that's darker means that there's less flux. So we're getting more flux at these certain lines. And this is OH sky emission. And so this is a big problem in the near infrared because these OH sky emission lines, they change really quickly. And so over the course of your observations, so over the course of a night, the OH skylines will be changing in brightness and depending on where you're looking in the sky, which makes it really difficult to remove. And so when we're observing in the near infrared, we often have this strategy where we dither between two different positions on our slit. So here's my attempt to illustrate this with just boxes in PowerPoint. Okay, so you have your slit, which looks something like this. And oftentimes the slits are 5 arc seconds or so in length, whereas in width, they're much shorter. And so you put your target in one position, and this is called position A. And on when you're observing, you can make sure to put it at an exact position where the A position always is. So then what happens is you can see the sky background in the rest of the slit. So then you take an exposure at position A, and then you switch and you move the target up to the top of the slit so that now the top is in, the target is in a completely different position and the sky is now in the bottom. And what you end up doing is you take exposures dithering back and forth between two positions. And so this is done in almost all near infrared observations. Even for imaging, for low resolution spectra, you'd always do dithering observations. So for example, if you're preparing for observations for the James Webb Space Telescope, you usually have to choose a dithering pattern for that as well in order to try to get rid of some of this sky background. And for James Webb, even though it's in space and it doesn't have Earth's air glow, there's lots of other sky backgrounds. The sky is just much brighter in the near infrared. So even if you don't have Earth, you're still going to get a much brighter sky. And so dithering is always a good idea in the near infrared. Okay, and you're actually not wasting any overhead time since you can add the target when it's in position A and position B. And so to get the spectrum of the sky during your observations, this is like real-time spectrum of your sky as it's changing, you can add the A in the B frame and then subtract the absolute value of the A frame minus the B frame. And this kind of gives you an estimate of the sky during your observations.
Aurora.
Yes.
You have one question here on the chat. It says, this is the reason to have two archives, A and B, in Carmenes?
Yes, exactly. In Carmenes, you'll see all of the time it says vis_A and vis_B. This means that the star was placed in the A position. And for the observations that I gave you, we were only looking at the A position because oftentimes if you are looking, so it depends on what kind of science you're doing, whether you do this dithering or not. So if you're just doing a single observation and you don't care too much about sky emission lines, you can just put the target on A and not do dithering. But if you really want to get the cleanest spectrum, you want to do A and B dithering. So for just our exercises yesterday, we just grabbed the A frame, and I didn't even check to see if the B frames were dithered. And so we just looked at the A frame. Yep. Okay. Yeah, that was a good catch. So I did say yesterday I would tell you about the A and B frames. Okay, so now we have, in our observing strategy, we've gotten rid of, or we've tried to get rid of the sky background. And we've also gotten rid of any sort of gain or change in how the response function works in different places in the spectrum, or sorry, in different places on the CCD. And we've also gotten rid of dark current. So those are kind of the main correction steps that we have to do. And so next, we want to extract the flux from the different orders. And so what we can use is the flats to also help us trace the orders. So the flats, they've been uniformly illuminated. And so it kind of gives you a really nice, way to check to see where all of the orders are going to appear on the CCD. And so what you usually do is you can take a different Y cross sections. So for example, this green line here, and you can plot all of the pixel values across this green line. And it's going to look something like this, where you don't get very many pixels, and then you get a large amount of pixels. And sorry, you don't get a very high signal, and then you get a large signal. You don't get much signal, a large signal. So this is what it would look like between the orders. And so from the flats, you can find where the orders are. And so what you do is every, I think for IGRINs, they say that they do every 40 pixels or something. So they'll put a green line here and then make a trace like this. And then they'll do it again in 40 pixels. And then they'll do it again in 40 pixels. And then they'll do it again in 40 pixels. And then they'll fit a polynomial for each order. And they save those positions so that later they know exactly where each order should go. So that even if you have a object spectrum that is pretty dim and it's kind of hard to tell exactly where the order is, we can use the positions from the flat in order to extract the spectrum from each order. Okay. So remember how I told you that in high resolution spectrographs, the slit length is much larger than the target. So if you're looking at a point source, the size of the target, it'll depend on the atmospheric conditions. So if you have good seeing, you can get much smaller point sources. But either way, the point source is going to be a lot less than 5 arc seconds if that's the length of your slit. And so versus if you have an extended source, so when we looked at the sheet that had been uniformly illuminated, it took up the entire slit. And so you can see that the orders basically have no space between them. But here, because the target is only at the bottom of the slit, you have a lot of more space between the orders. And so it is a little bit more complicated to extract. It's a bit more complicated to extract than just using the exact trace orders and combining everything in it if you're looking at point sources. But we can still use the traced order to help. And so what we do, I tried to draw a line that would trace the top and the bottom of where the order would be extracted from the flats, but my line looks really bad. But basically the green lines, I was trying to do an example here where that would be what we would get from our polynomial fit for that order. And then we would use a bright object. So oftentimes you're going to look at a bright star before you look at something dim, just to check. And so we can look at the bright star, and when it is in position A, which is a designated position, the star should always be on position A at a very specific place. We can look at how many pixels within the trace, how many pixels are illuminated. And so this is kind of called refining the aperture. And so the aperture you should try to have encompass all of the pixels that have the target's light, but try to minimize the number of pixels that have any sort of sky background, because that'll introduce noise. And so you kind of have to try a few different things, and you can plot this up when you're doing the reduction to find the best aperture for your targets. And then when you do this on a bright source, you can use the same aperture for the rest of the night for any dim sources. As long as the seeing conditions don't change too much, it should be basically the same throughout a single night.
Sorry to interrupt, Aurora. You have another question here in the chat. It says, why a polynomial instead of a Gaussian functional form, or any? I will add to that question.
Yeah. So a polynomial is just a very easy way to do it, and you don't want, I guess a Gaussian wouldn't necessarily be good, because the shape of these lines might not necessarily exactly fit a Gaussian. You can see that they kind of peak not quite exactly in the center, and then it falls off on this side a bit faster than it falls off on this side. And so, yeah, you don't want to restrict it to a Gaussian, and a polynomial fits the lines pretty easily and is very, yeah, you can just store the coefficients for a polynomial and pretty quickly come back to it. So that's why I use a polynomial. It's just kind of the easiest way to do it. Okay, right. So then once you have your new aperture that should encompass all of the target pixels for your point source, basically you can just add up all of the pixels that have the target's light along the y direction, and that will basically extract your spectrum. So what that looks like is something like this. This is the extracted spectrum from a single order. So from, let's just say we extracted the order between the green lines, and we've added up the flux in the y direction at each x pixel. So here we have the x pixels going from one side of the CCD all the way to the other side of the CCD. And at the edges of the CCD, you can see that we get fewer counts, and at the center we get more counts. But you can see already that on top of the shape of this, you can see that we have some absorption lines here, maybe some widened absorption lines over here, and some other things that look like a spectrum. And this shape here that the order gets is called the Blaze function. And it's just naturally an effect that you're always going to get when you're looking at the shell CCD. You're going to get all of the orders are going to look like this. And so we'll talk about later how you correct for this. Okay, so next, I'm going to talk about how you get a wavelength solution. And so if you remember, well, let's see. So here we just have x pixels, and the x pixels are just from the CCD, but we don't actually know what wavelength these x pixels correspond to. So in order to figure out what wavelength each x pixel corresponds to, you usually take exposures of an arc lamp. These are arc exposures. And basically what the arc exposure is now instead of looking up at the sky or looking at a sheet that's been uniformly illuminated, we take a spectrum of an emission lamp. And the emission lamp is chosen so that there's lots of different lines. So you can see all of our emission lines. They're showing up as bright white lines. And you want a lamp that has emission lines in every order that are pretty well dispersed. And so when you take an exposure of your arcs, you know what is in your lamp, and you have a very precise wavelength of each of those lines. And so then you do the exact same, well, I'll do that in a second. And so you know the exact wavelength of these lines. And in the near infrared, oftentimes it's thorium-argon lamps that are used. Sometimes in the red end of the visible, these are also used. And so we know the exact transitions of each thorium-argon lamp line. And so then we can map, say that this line is at 2.3 microns. Then we know at this exact position in the target corresponds to 2.3 microns as well. So the usual procedure that you use to do the wavelength solution is you basically go through the exact same procedure that we've already been doing, except for this arc lamp. And so you take an exposure of the emission lamp, the thorium-argon emission lamp, and again, you want to always make sure you do more than one exposure in case something goes weird in your one exposure. And so you take this spectrum 1 to 3 times, and then you do the same pre-processing steps where you subtract the dark frame, you then divide by the normalized flat field, and you medium combine all of your arcs together. And then again, you use the same polynomial that our same flat polynomial. And since the argon lamp the thorium-argon lamp takes up the entire slit, we don't have to worry about this smaller aperture problem. We can just add up everything along the x direction within each order. And so we extract the spectrum that way. And then we can determine the x pixel position of each line. And the lines have known wavelength transitions. And then again, we use a polynomial just because it's easy. So we fit a polynomial, and this polynomial basically converts the x position to a wavelength. And for most of the time you do use an arc, but sometimes in near infrared observing, you don't actually have to use an arc. You can actually use the position of your sky emission lines. So if you don't need extremely precise wavelength solutions, then you actually don't have to waste any of your observing time going for arcs, because we know the wavelength transitions of OH emission lines. This is not quite as precise as doing an arc exposure, because these OH emission lines, they can have small amounts of velocity, and so you're not going to get quite as precise as you are from a lamp. But if you don't care about an extremely precise wavelength solution, then you can skip the arcs and simply use the OH sky emission in the near infrared only, because this mostly affects the near infrared. So depending on your science, you can prioritize different things. Okay, so then what happens when you get a wavelength solution is it converts the x pixels on the x-axis of this plot into wavelengths. So this is the exact same plot that I showed before, except for now we've mapped each of the x pixels to a wavelength, and this is just a single order. Okay, so Again, the colors here don't mean anything, it just plotted. And so here I'm showing you a full reduced, but before any of the pre-processing steps, spectrum of from Igrans. So this is in the near infrared, so it's about 1.4 to 1.8 microns. So this is the H band. And you can see that we have all of the wavelength solutions. So each order has a wavelength, but each order still has this characteristic blaze function shape that has not been removed yet. Okay. And we just have counts on the y-axis here. Okay, so next I'm going to talk about how we can go from something like this, which has still noise, it has telluric features, it has cosmic rays, and it has this overall shape here, into kind of the final spectrum that you're used to seeing. So one of the things that is the worst for observing in the near infrared is absorption from Earth's atmosphere. So this plot is showing where the different lines from Earth's atmosphere mostly get in the way. So, okay, here we have in green, this is ozone. And in blue is H2O. And those are kind of the main absorbers in Earth's atmosphere. You can see there's also CO2, but it's not quite as bad as the water and the ozone. So you can see that at wavelengths blueward, I don't like it. Okay. At wavelengths blueward of 0.3 microns, so that's past the visible. Basically, ozone completely wipes out any light. Ozone absorbs everything blueward of 0.3 microns. And so that's why people talk about how ozone blocks out UV radiation, and this is good for us not getting sunburns, but it's bad for observing from the ground in UV wavelengths. But then from about 0.3 to 0.5 microns, we have very little of any other absorption. You can see that there's barely any water, there's barely any CO2. And so this visible area of the spectrum is pretty good for observing. But once we get to about 0.8 microns, we start getting these large absorption features from water in Earth's atmosphere. So there's a big one at about, okay, I have to work on getting rid of this. There's a big feature at about 0.96 microns, right shortward of 1 micron. And there's another one here, another one here. And actually these features define what we normally call the near infrared bands. So we have the J band, the H band, and the K band are these kind of observing windows in between the, J, H, and K are the observing windows between the water bands in Earth's atmosphere. And the overall slope of this is just caused by continuum scattering. And so even though there aren't any telluric lines, you do get scattering. And so you do get less light coming through at blue wavelengths. Even though there's not anything that's particularly in the atmosphere absorbing there, it's the scattering processes that cause this decrease in transmission as we get blueward. So in the optical, it's not that important to correct for this Earth's atmosphere absorption. But in the near infrared, it's extremely important to correct for this telluric absorption. Okay, so looking at this in a bit more detail, zooming into the wavelength regions that we normally talk about. Here's kind of the main optical region. So from about 0.3 to 1 microns. This is usually what we refer to, anything in this region is optical or visible spectra. And again, here's the O3 feature, which basically kills transmission, blueward of 0.3. And then the main features here is we see that there's an oxygen, an O2 band, another O2 band, and then some H2O bands, O2, 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 H2O, H2O, H2O. But still, you get pretty decent transmission throughout the optical. But now if we change to the near infrared, again, here we're seeing these bands. And at 1.4 microns, we basically get zero transmission. So nothing even up here went to zero transmission. Here we get zero transmission. And again here, at 1.8 microns, we get zero transmission. Again here, all because of water. At 2.5 microns, we get zero transmission. And then going into the mid-infrared or the far near infrared, you get other absorption bands from nitrogen, oxygen, and it's really difficult to observe these bands from the ground. And so there are very few telescopes that will do anything with wavelengths blueward of about 3 microns. So all of the near-infrared high-resolution spectrographs are going to focus on the J, H, and K bands for the most part. So the K band is located in between these two water absorption bands. So here's the K band. We have the H band here in between the water features, and then the J band. And so the Carmenin spectrum that we worked with yesterday went from 1 micron to 1.8 microns. The IGRIN spectra that I've been showing you use the H band and the K band. And so these two. And there really aren't any ground-based spectrographs that will do much over here, just because it's so difficult to get transmission. And so this is why it's so important for telescopes like James Webb Space Telescope, because we're going to this space, and so we can actually observe in this wavelength region without Earth's atmosphere getting in the way. So there's a few different ways that we can go about correcting for Earth's atmosphere. And one of the main ones that we can do in the near infrared is we can use A0 stars for telluric correction. So A0 stars are just hot stars. And basically A0 stars are good because one, they're bright. So you don't have to spend too long looking at them to build up a lot of signal. And also they basically look like a black body with a few hydrogen absorption lines on top of that. So you can see it basically has a clean spectrum with some deep hydrogen absorption lines. And by observing an A0 star at the same or right after or at the a very similar time that you observe your target, you can get a extremely localized reading of what the telluric or what Earth's atmosphere is doing at the same time. And the reason that we would use an A0 star instead of just a model of Earth's atmosphere is because depending on where you observe and at what time you observe, the atmosphere can look really different. So if you're observing on Mauna Kea in Hawaii, there's not that much water, versus if you're observing in Spain, you might have more water, and clouds and water humidity features can change every few minutes. So on the order of 20, 30 minutes, you can have a very different telluric spectrum. And so this makes it a little bit difficult to correct for tellurics if you really care about removing all of that all of that absorption. It can make it really difficult. And so by doing these A0 stars and observing them right after you observe your target, you can kind of see the exact amount of absorption that you're getting at your location at your time. So the usual procedure that we use if you want to correct with an A0 star is you would observe your target star, so whichever star you would like for your spectrum. And then you observe an A0 star at a similar air mass, which means at a similar altitude and at a similar right ascension declination. So basically as close to the target in space as you can. And the reason that you need to really care about the air mass is the air mass tells you how much of the Earth's atmosphere you're looking into. If you're looking straight above you, you're only looking through a small amount of Earth's atmosphere. But if you're looking on the horizon, the amount of Earth's atmosphere you're looking into is much bigger, which means that you're going to get a lot more telluric absorption. And so the main thing that you need to do is observe a A0 star that has a similar air mass to your target star. Unfortunately, this does add a good amount of overhead time to your observation. So you have to slew the whole telescope to this new star. You have to make sure the star is on the slit. Then you have to observe the star and build up a large amount of signals. And so this can not quite double your observing time, but it can add maybe a third of your observing time. And on a really big telescope, this is wasting a lot of time. And so again, how you plan your observations depends on what type of science you want to do. If you're really interested in specific absorption lines that are near a water band, and you really care about the exact line depth, then it would probably be a good idea to try to get the best correction for Earth's atmosphere. So maybe observing an A0 star is the best thing to do. But if you don't care as much, then you don't have to do an A0 star. You can correct for telluric absorption afterwards. And if you're kind of in the middle, you want to remove some of the telluric absorption, but it doesn't need to be perfect. You can share A0 stars between a bunch of targets. So maybe every 3 or 4 targets that you observe one telluric standard star. And just make sure that you have a similar air mass standard star for each of the targets that you look at. Okay, so looking at this in real time, so here are some examples for what a telluric correction with an A0 star looks like. So here is your, at the bottom, here is your A0 star in a single order. And so remember here, again, we have the blaze function. This has not been corrected for in this A0 star. And then it kind of looks like you have black body absorption, and then you have some of these hydrogen lines built on top. But we know precisely the spectrum of an A0 star because it basically should just be hydrogen lines with it should be a black body continuum with hydrogen lines built on top. And so we can remove these hydrogen lines and get a good estimate of the telluric spectrum. So that's what we're showing here. And here's a model of what the atmospheric transmission looks like in this order. And so you can see that over here we have probably some water lines, and the telluric spectrum that we observed also has those. And over here again we have another water band head. And again, the telluric spectrum has those. So yeah, telluric contamination at the time and location of the target can be separated out from the A0 star, which is shown here. And this leaves a telluric spectrum as well as a measurement of the blaze function. So another benefit for doing this A0 correction for tellurics is that you get a correction for the blaze function at the same time. So here's an example from, again, one of the IGRN spectra from my data set. And here we have our original spectrum. And then this is in orange, we have the spectrum after the telluric division. And you can tell that basically by dividing, we increase the noise over here. Well, we don't increase the noise. We get very few counts over here. And so basically that looks like an increase in noise, but it's really the same amount of noise. It's just that you can see it much better now that the blaze function has been removed. And you can see that some of the telluric features have been removed. So here in the original spectrum, you have lots of lines here. And then in the corrected spectrum, you can see that basically we have a doublet and a single and a single, and a lot of these lines in the middle have been removed. And so after the A0 division, we get a spectrum that has been removed of any telluric contamination, and we've removed the blaze function, so any shape of the spectrum. So you can also do telluric correction without A0 stars. And in the optical, like I showed before, there is a bit of absorption from Earth's atmosphere, but it's never as bad as in the near infrared. And so people, when they observe high resolution spectra in the optical, they don't waste the time to observe A0 standard stars that you would in the near infrared. So in the optical, if you want to remove any telluric lines, you can often do this with modeling tools. Like MolecFit is one of the modeling tools that you can use, which basically models, takes a model of the telluric absorption in Earth's atmosphere and fits it to your spectrum in order to do the best removal of the atmosphere as possible. So these are all synthetic or model transmission spectra. And it takes a bit of time because at high resolution, you're trying to fit the spectrum in a small region. So you choose a region where there's a good amount of telluric absorption, but you want to make sure that there's not very many absorption features. So this is a good region because it's mostly clean of absorption, stellar absorption features, but it does have telluric absorption features. And then you fit the model trying to fit the exact line profiles. And it creates a model and then it divides it. So in this example here, the black is the original spectrum, and then the telluric corrected is this red spectrum. And you can see that for the most part, it does a good job, but sometimes it adds these extra increases in flux where it has divided out a bit too much of the telluric region. And overall, it doesn't quite do as good of a job because when you're doing this in real time, you can kind of see how the different line strengths change based on the humidity and the changes in humidity. And when you're doing it from a model, you are often going to get these kind of features where it doesn't exactly fit the line spread function and the line strengths of all the individual lines. But it does a pretty good job of removing, well, you can see here, it does a pretty good job of removing most of the telluric absorption.
Sorry, Aurora, you have a question in the chat. It says, why is it common to have less counts at the edges of the spectrum, even in X-ray spectra? Does it has anything to do with the frame of the CCD?
Yeah, so there's two reasons why you get less counts at the edges. One of it has to do with the response function of the CCD. So at the edges, the response function of the CCD is not as good. But then the other reason is when you spread the light out. Can I answer this in a second? Because I want to go back to my other slides. So I'll just finish this section and then I'll answer that before the break. Okay, yeah, I just wanted to say the last part for this with the telluric correction is since the blaze function is not removed with tools like MolecFit, you need to do something to remove the blaze function. So this is fit it with a polynomial to remove the shape of that. Okay, and then let me go back to my previous slide. Yeah, so the other reason why you get less absorption on the edges just has to do with how when you spread out the light and you're looking at the orders, basically you get one wavelength that's completely maximized, and then based on the fringing pattern, it kind of falls off. And so, yeah, it's both because of the CCD and because of how orders basically are created with fringing patterns, where you get the most amount of light at the very center, and then you get less light at the edges of your fringing pattern. And so, yeah, you try to create the most compact fringes as possible, but you're always going to have some sort of like trail off towards the end. And you can kind of even see this here where you get the brightest amount of light and then it kind of trails off as you're going to the edges of each order. Okay. Cool. So I think that I will stop here for the first part of the lecture. And if anybody has any questions, I'm happy to answer them now, or think about them and I can answer questions again during the next session.
Yeah, I don't see more questions right now on the chat, Aurora. So let's take a 15 minutes break and we will be back at 3:30 your time, 3:15 your time, 9:15 Colombian time. So see you in a minute.
Okay, great. Thank you.